So basically we have a cart. This is kind of like a roller coaster, amusement park type thing. And the cart goes up to the top of the hill. Actually, let's not make it a roller coaster or amusement park thing. Let's make this like the streets of San Francisco, right? You guys have all seen those car chase scenes when the car is kind of going through and catching air on each one of those things. If you've ever been driving, either yourself driving or been in the car, and you go over the top of a hill and your butt comes off the seat a little bit, or you get a little bit lighter in the seat. Some of you have this reflex to be like, yeehaw, like, or something like that. If I'm driving with somebody, I make the Dukes of Hazzard horn sound where I'm like, like when you go over the top. But whatever it is that you do when that happens, the question I have in this particular problem is, if you're going over the top of a hill that is part of a circle, so it's only a portion of a circle, but if you're going over the top of a hill where the radius of curvature at the top point is 24 meters, I'd like to know what the maximum speed that you can go, what's the speedometer in your car, if you will, without the wheels leaving contact with the road. So certainly you can go through really fast, and that would just turn this into a jump. But my question ultimately is, what's the maximum speed to keep your tires on the road? Are there any questions about the nature of what I'm asking? We write our dynamics equations after we've drawn the free body diagram, but I'd like to ask the question, is the sum of the forces acting on the car if it's moving at a constant speed at the top? So its speed here is equal to the speed here is equal to the speed here. Is the sum of the forces acting on it equal to 0 or not equal to 0? What do you think? How many people think it's equal to 0 by show of hands? Constant speed, equal to 0. How many people think it's not equal to 0? Okay, what is your evidence, Peter, for the fact that it's not equal to 0?
It's moving in a circle, so therefore it's accelerating.
Beautiful. End of discussion. That's all you need to say. Dude, it's turning, stop thinking, it's accelerated. And if it's accelerated, the sum of the forces cannot be equal to 0, so whatever our free body diagram looks like, it should support that. What would the free body diagram, Nikki, look like if it were at rest? The car were just sitting there and not moving. What would the free body diagram look like?
It would just have like mg and normal force.
Mg and a normal force going up. And as the car starts going through the turn faster and faster, which one of those forces is going to change? Let me ask you this. Where's the center of the circle?
Below.
Below it. So what needs to be the direction of the net force acting on the cart moving through the circle?
Down.
Downward. There has to be a leftover force going downward. We call leftover forces that are causing circular motion. We no longer call them net forces. We call them centripetal forces. Okay, so let's take a look at this. We need to have a leftover force. We're going to call it F sub c, directed radially inward. In this case, in this orientation, it is down. Which one of those forces is negotiable? Weight? Is the earth going to pull on the object with less force?
No.
No, this is non-negotiable. But as you go through the turn faster and faster, the normal force gets smaller and smaller. You guys need to remember that your experience with weight is actually the normal force. Right now you're like, oh, I feel about 150 pounds. Well, what you're feeling is the floor pushing up on you with 150 pounds. That's what you're feeling. If we take you and we drop you at the Star Blaster at Canopy, is that the one that? Okay, if you drop, you're 150 pounds, but you're weightless. You're still... The earth is still pulling down on you with 150 pounds, but there's no normal force pushing up on you, which is your experience of weight. And so therefore, the normal force is adjusted. What's the largest leftover force I could possibly have?
Mg.
Mg. When the normal force ebbs away to nothing. You can't have a larger centripetal force than Mg. And mg is the centripetal force, which we know is equal to mv squared over r. And m, the mass of the car, and the radius aren't changing, and so v maximum occurs with a maximum centripetal force, which can only be as big as mg. We can't make it any larger. Okay, so now we've drawn a free body diagram. Okay, let's regroup and take a look at the solution to this. After our first discussion, you should have recognized that the only force acting on the object at the top at its maximum speed was its weight, and the normal force had gone to 0. The sum of the forces is not equal to 0. That gives us an expression that looks like this. Keep in mind that mg and the centripetal force are radially inward. So therefore, positive is radially inward. So we're going to call downward positive in this case because it's towards the center of the circle. We don't give it a negative sign. So we can say that mg is equal to fc. The mass cancels out. We didn't need it. That speed doesn't change whether you're driving a Toyota Yaris or a Hummer H1. The wheels will leave the ground at the same speed for both of them. We get an expression that looks like this. The maximum speed is equal to the square root of g times r. Plugging in our numbers in, we get 15 meters per second. Questions on that? In this next problem, we have a roller coaster loop. The coaster goes down the loop, and down the hill and around the loop, and then completes the loop like this. You're going to be given speeds at points A and B. A is going to be at the bottom of the loop, and point B is going to be upside down up there at the top of the loop. And the speeds are 26 at the bottom and 17 meters per second at the top. The radius of the loop is 18 meters. The mass of the cart is 350 kilograms. The question is, what is the ratio of the normal force at A compared to B? So let's do, the normal force at A compared to the normal force at B. So how much larger or smaller, how many times larger or smaller is the normal force at those two places? Short 2-minute discussion before you complete your free body diagrams. I've got a bucket at the front of the room. The bucket has a string attached to it. And I'm going to fill the bucket with some water. And I want to ask you guys a question about, can I turn the bucket upside down and not have water come out of the bucket?
Yes.
Okay, what do I have to do to it? Okay, so I need to swing it around. So there is going to be a speed. Do I want to swing it fast or slow? Okay, fast. The faster I swing this bucket, the less likely the water is going to come out of the bucket. So I can certainly get it to go around in a circle if I moved it really quickly, and I don't have to worry about any water coming out of the bucket at all. The problem is if I slow down and there is a minimum speed. Watch very carefully and listen. Listen to the sound of the water. Right now you can't hear it. That was a little aggressive. Okay, so when the bucket is at the top of the loop, you can see slack in the line. You guys should know that ropes can only pull. There can only be tension. So at the top, the direction of the tension force can only be down. So there is a minimum speed at the top of this loop, not a maximum one. The other one was a maximum one. Now, I'm talking about a minimum speed at the top because the direction of the tension is downward. So you're going to see the slack in the line. Now you don't have to listen. Just look at the slack in the rope. Right there. You can hear the water right there. That's a minimum speed. I can go much faster than that if I want. I got nothing to worry about. But there's a minimum speed. Think about what your free body diagram looks like at the top of the circle with the tension and the weight vectors. Because there's a fundamental difference in a vertical circle than a horizontal circle. I want you guys to think off to the side. I'd like you to draw free body diagrams of this bucket at the top of the circle and a free body diagram of this bucket at the bottom of the circle. Checking in for the free body diagrams of the bucket. Jared, what do you have for us? What are the forces or force acting on the bucket, let's say, at the bottom?
Well, mg is always acting downwards.
Mg is acting downwards. Could I say that mg is radially outward or radially inward? Outward. And what's the direction? What other forces are acting on the bucket at the bottom?
The normal force going up the tension.
Okay, good. So there is no normal force, but there is a tension force in the string. How does the tension force compare to the weight force at the bottom?
They are equal.
They're not equal. No. They're not equal. Justin, why aren't they equal?
Because of the buckets moving in a circle.
It's moving in a circle. There has to be a leftover force. So this radially inward force needs to be larger than this one. And we don't draw leftover forces on a free body diagram, which is why I'm going to kind of draw it off to the side. But the tension force needs to be larger than the weight force to have some leftover radially inward. Notice what happens at the top. Micah, what are the forces acting on the bucket at the top?
mg.
mg. What's the direction of mg? Radially inward or radially outward? Inward. Notice there's a difference. So what happens to the tension force? It's going to be smaller at the top, which is why probably most of you are like, well, that's why there's less tension at the top of the loop than there is at the bottom. If I were swinging this really fast, there's much more tension down here than there is at the top of the loop. And that is because weight is helping turn in a circle at the top, and it's working against you at the bottom. That's a big idea in vertical circles. I'd like you to apply that to the roller coaster problem here. Go. Make sure your free body diagrams are ready to go in 60 seconds. Okay, let's go through this problem. We've drawn two free body diagrams here. We've recognized that at the top, both of the forces, the normal force and the weight force, are radially inward, which is reflected in our dynamics equation. So when we look at the top, we see that both mg and the normal force are positive. That might feel a little weird. We're used to calling things in the downward direction negative, but radially inward is now positive in a circle. That's equal to F sub c, and I get an expression for the normal force that I can work with, and I get 2200 newtons. I truncated for sig figs here. Technically, you're not supposed to do that till the very end of the problem, so you might have slightly different ratio than I got. But 2 sig figs, 2200 newtons. And when I look at point A at the bottom, the normal force is the only positive force. The weight force is negative because it's radially outward. You have to put that into your dynamics equation or your model will be off. That's equal to our leftover force, our centripetal force. Solving this algebraically for our normal force gives us an expression that yields about 17,000 newtons, meaning that the ratio of the normal force, or your experience with weight at the bottom compared to the top, is 7.7, meaning that you're going to feel 7.7 times heavier at the bottom than you do at the top. A combination of two things are at play. You're moving at a slower speed, but also you're upside down. So of course, that is going to affect the interactions with the normal force. Are there questions on this particular problem here? We're going to take a look at a slightly different problem than you've seen so far dealing with circular motion. Here's our big, beautiful blue home, planet Earth. And there are a lot of satellites. There are a lot of things. Most satellites are artificial, but of course there are natural satellites like our moon. But in this particular case, we have a spy satellite. A spy satellite tends to have a lower orbital altitude above the surface in order for the optics to be optimized. The idea is you want to be able to see what's on the ground, so you keep the satellite as close to the Earth as possible. That means its orbital speed is going to be fairly fast. The International Space Station, which is at a very low Earth orbit, like spy satellites, makes one complete trip around the Earth in about 90 minutes. So it's going pretty fast. It's only above your head and be observable, and for that reason, it's able to observe you for only a few minutes. So it kind of has this window where it can kind of check in on you, take pictures of what you're doing, and then it's over the horizon, so to speak. You can't see it. So this particular satellite has an unknown mass, and it needs to be inserted at this relatively low altitude above the surface of the Earth of about 350 kilometers. The mass of the Earth is known. It's 5.98 times 10 to the 24th. That's a concept that will always be given to you. You don't need to memorize it. But also, you need to know that the radius of the Earth is 6,380 kilometers. So now you can see that I did not draw this to scale because that's a much larger number than this, and so they shouldn't even be close in length. But the point that I have is this, or I should say the question that I have is this. What needs to be the velocity of the satellite in order to achieve a stable orbit? If we go too fast, the satellite is going to careen away from the Earth and get in a larger and larger orbit. If we go too slow, then the satellite's going to crash back down into Earth. This is almost kind of like the Goldilocks problem. We need an orbital speed that's just right so that the altitude of the satellite remains constant over the surface of the Earth. I'd like you guys to start by just drawing a free body diagram of the forces acting on the satellite. Free body diagram of the forces acting on the satellite. Holly, what did your group come up with for a free body diagram? If this is a free body diagram of that satellite.
We had mg.
Okay, good. I'm gonna use, instead of mg, I'm gonna just use the force due to gravity, which is mg. You can also call that weight, but it's a force in newtons, and it should be radially inward, which means that if I'm drawing a free body diagram of the satellite in this position, it's gonna be to the left. Other forces acting on the satellite. That's it. There's no drag, there's no friction, there's no string attached to it. There's only one force, the force due to gravity. So what is your centripetal force? The force due to gravity. All right, see if you guys can figure it out. What needs to be V? I'll take your question in 1 sec. I want to start by acknowledging that everybody kind of started in the same place, except after this point, some groups went and said mg is equal to mv squared over r, which works until you leave Earth. And if this satellite were orbiting some other planet where g was not known, the acceleration wasn't given to you, you would have to use universal gravitation to express the gravitational force. What this is in the red box right here is often referred to as the satellite equation. You should not memorize it, but you should know how to derive it. So if they ask, and some of the key words that the College Board likes to use are things like stable orbit and things like, if you hear that and you're like, okay, then I need to work on using the satellite equation. And it just comes from setting the gravitational force equal to the centripetal force. I put subscripts where E is Earth and S is satellite. So the mass of the satellite drops out. One of the R's on the left cancels with the R on the right. And I'm left with this expression, the square root of G mass of the Earth over the radius is equal to my tangential or linear speed. I can then plug my numbers in. And often a mistake is here. Kids lock on to the idea that the satellite is 350 kilometers above the surface, but the satellite's orbit does not drive into the surface of the Earth like that. That is not the radius of the circular orbit of the satellite. So you then have to add that to the radius of the Earth and then convert to kilometers. A lot of kids will forget that step as well. Sorry, convert from kilometers to meters. So make sure that you add those two, the distance above the surface with the radius of the Earth, convert to meters, throw it into your satellite equation, and you get about 7,700 meters per second. I converted that to miles per hour just so you guys would feel more comfortable with how fast that is. That's 17,000 miles per hour. I'll take Shai's question first and then Drew.
So, how far off would we have been if we didn't use the universal gravitation?
You would have been spot on. You should get the exact same answer. If you just said mg equals mv squared over r, I'm just saying that that's limited for when you know g. But if you don't know g, then you can't use that.
We're a solid 400 off.
Yeah, 400 meters per second off.
Okay, I'd have to check your work. Did anybody else use mg equals mv squared over r? Did you guys get 7,700?
No, we got 8,100.
That's what we got.
You got 8,100. Ah, this is beautiful.
It's outside the Earth. So
yeah, we're far enough away from the Earth's surface that the acceleration due to gravity is not 9.8 meters per second. So this is beautiful. Here's a mistake that I made, right? So the G is not 9.8. It is at the surface, but 350 kilometers further away from the surface, and it's probably going to be like 9.2 whatever. I don't know what it is, but it's going to be close to 9.8, but not 9.8 because you're far enough away that it's been affected slightly. So that's why you guys are getting numbers that are slightly different, which is so cool. So, I guess that the answer is, hey, you can't just substitute mg unless you solve for g first. You could solve for the acceleration due to gravity at that altitude above the surface by having used gravitation. So you could say Fg is equal to g m1 n2 over d squared, and the gravitational force is equal to mass times acceleration, or g, and then you would have solved for g that way. But by the time you've already done this, you might as well have just set up the satellite equation in the first place. Awesome. All right, so we caught that little mistake there. Are there any questions on what we've done here? All right, let's stop there for a second.